So our symbol for specific heat is a lowercase c. Okay? Not a capital C, because what is capital C? Celsius. And that is like, I mean, all of them are important that you write the symbol correctly, but I can't explain to you how important it is that you write the specific heat symbol correctly as a lowercase c, because we work with Celsius in our specific heat formula sometimes. And so you can't be like doing that. It'll be wrong and it won't make sense. So again, our symbol is a lowercase c. Units typically are reported in joules per gram Celsius, but also, I know some of you guys might be like, well, that looks like a lowercase c, but what do I have next to Celsius? The degree, okay? That's another thing. So what this is saying is you have joules times grams times Celsius, okay? All of this is dependent on the state of the substance. Different states will have different specific heats. Now, what does it mean by state, Hattie?
Is the state like solid, liquid, or gas?
Good. So not like if it's found in Louisiana or Missouri, right? It's the state, okay? I guess that could depend because the state would change depending on if we're in Texas. Well, the state could literally be 3 different things in one day in Texas. You just never know, okay? So as specific heat can be used to identify, it is considered an intensive physical property, an intensive physical property. So if we were to look at this chart, right here we have liquid water, solid ice, and water vapor. All of that is talking about H2O, okay? There's the different states, and you have your different specific heats, okay? If we were to ever, like, I'm not expecting you whatsoever to have this chart memorized. We would give you the specific heat of something if it's needed in the problem. Now, we could also ask you to find the specific heat. Obviously, we wouldn't give you that, but we would give you all of the tools needed in order to solve that, okay? So I don't want you to worry about memorizing the specific heat of liquid water. That is 4.18, okay? All right, substances with a low specific heat are good conductors because they have large temperature changes with small energy changes. So again, substances with a low specific heat are good conductors because they have large temperature changes with small energy changes. Okay? Substances with a high specific heat are good, what you think? Insulators, good. Because they have small temperature changes with large energy changes. So let's read this example. On a sunny day at the beach, why is the sand hot but the water is cool? The specific heat of sand is 0.78 joules per gram Celsius, and the specific heat of liquid water is 4.18. So I want you, before we talk about this, I want you just to talk with your tables. Talk with your tables about this example and talk about why is the sand hot but the water is cool. I'm going to give you about 30, 45 seconds. Go. Okay, somebody raise their hand and tell me, on a sunny day at the beach, why is the sand hot but the water is cool? And not everybody at once. Yes, Heather.
Because the sand has a low specific heat, it conducts more of that heat, so more of that heat will become hotter.
Good.
The water has a high specific heat, and then it wouldn't keep that heat in.
Yes, awesome. So basically, sand has a smaller C value, which we know is specific heat. So you have greater changes in temperature when absorbing the same heat amount. Okay? So again, sand has a smaller specific heat value, so our changes in temperature are greater when it's absorbing the same amount of heat. Okay? Because sand and water, that heat is the same all throughout. But the way that the water absorbs it is different than the way that the sand absorbs it. All right, calorimetry. Calorimetry is a technique used to determine the heat change in a reaction or process. However, because we can't measure heat directly in a lab, we instead measure the magnitude of temperature change that is caused by heat flow. So a calometer is a device used to measure the heat flow. And that's what we're going to do for our lab. Okay? It's a really fun lab, and in AP Chem you take it even one notch further. Some of my favorite labs in college were calorimetry labs and titration labs, and you'll get to do all of those things this year. Okay? All right, so we have a formula for calorimetry. This formula is quite frequently referred to as MCAT. So for my people who want to be a doctor, what is the test you take? What? The MCAT, right? So it's super easy to remember. And the reason it's referred to as MCAT is because this is what you have. So specific heat, okay, is right here. You have your mass, which is in grams. So if I were to give you a mass that was in kilograms, what would you have to do? Convert it. What happens if I gave you a mole value? What would you have to do? Turn it into mass. Okay? And then you have delta T, which is the temperature change. It can be in Kelvin or Celsius. But if you have one in Kelvin and one in Celsius, what do you have to do? Convert. Okay? And it's final minus initial. Not initial minus final. It's final minus initial. Okay? And then that equals your delta H, which is enthalpy, and your mass. Okay? Can I get a volunteer to read this saying? Yes, Addie.
Keep in mind, you must measure mass to actually use this one. Therefore, a specific heat is given in grams, and the mass must be grams. Also, a specific heat is given in joules, the enthalpy must be.
Does everybody understand that? That's kind of just talking about what I just said. If I give you something in a specific unit, you need to make sure all of the units are given throughout. Okay? All right, so simple calorimetry. The basic idea of a calometer is to measure what is happening with the surroundings to make assumptions on what is happening within the system. Okay, so this is basically a setup, and this is what we are going to do in our lab. So you have your thermometer, which is right here, and it goes all the way down. Okay? You then also have your glass stir, a cork stop, 2 styrofoam cups that are nested together. And then you have your reaction mixture that is in the solution. So you can see your styrofoam cups that are put together. Okay? And this is going to be like a really cool lab. So please pay attention. Hopefully we don't have an ice day, because our other lab we were supposed to do was going to be really fun too. So I want, using this picture of a calometer to the right, I want us to identify the system and the surroundings. So what do we think our system is? No, but good guess. So again, the basic idea of this is to measure what is happening with the surroundings to make assumptions on what is happening with the system. So what do we think our system is? The reaction. Okay? Our surroundings are the cups, the stopper, H2O, and the thermometer. Thermometer. Okay? So if the temperature of the water, the surroundings, goes up, then the process, the system, must have released energy, which means the process is what? Good. If you did not know that when we release energy, it's exothermic, you need to make sure that you look back and review your notes from last class, or the quiz you take next class will be rough. So if the temperature of the water or the surroundings goes down, then the process must have what? Absorbed energy, which means that the process is good. And just really quick, so when the temperature of the water, the surroundings, goes up, what does it feel? Feels what? Cold or warm? Feels warm. And then if our temperature goes down, then it feels cool. Okay? Just some things to remember. All right, so the big assumption with simple calorimetry is that the container is perfectly insulated, and the heat change, which is the system, of the process is equal to the opposite heat change of the surroundings, which is water. So we have Q system equals negative Q surroundings, or negative Q system equals Q surroundings. So at this level, we are going to assume that all of the heat given off by the process will be absorbed by the water, or vice versa, and that no heat was given off to anything else in the setup. In reality, there is some heat absorption by the calorimeter itself, as well as some heat loss to the surroundings, as it is not a perfect insulated system. Okay, we're working with styrofoam, and we want you to see the process. Okay? All right, so now we are getting into math. Yay! Okay. So, can I get a volunteer to read this example? Not everybody at once. Thank you. Heather.
A piece of metal with the mass of 15 grams was sitting in a boiling water bath at 100 Celsius. The metal was removed from the boiling water and quickly added to a sample of water in the styrofoam coffee cup calorimeter. The water in the coffee cup had a mass of 100 grams and was at an initial temperature of 25 Celsius. The specific heat of water is 4.184 joules per gram Celsius.
Perfect. Thank you. So, before we do any math, let's answer like A and B. So it says, what will happen to the temperature of the metal once placed in the calorimeter? Okay, it will release heat, and what will happen, though, to the temperature? It's going to cool down. So then, what will happen to the temperature of the water once the metal is placed in it? It will warm up. Okay, so before we do all of these, we need to write down some information. And one big thing, and I know like on your test and quiz, this will be like really important, so that way you don't get the metal and then the water confused. So let's first use our, literally losing my mind, our formula. What's our formula? Delta H equals MCAT, MC delta T. Okay? All right, now let's write down some of the information that we have. So I'm going to draw our piece of metal. Okay? So I have metal, T initial, and then T final. Okay? So what was our weight of our metal? What was our initial temperature? 100 degrees Celsius. And then what was our final temperature? What was it? Okay. Next, I'm going to do it in a different color just so we can see it. Our water. Yes, that's water. I know it doesn't look like it. I told you guys I'm not Picasso. So I'm going to place our metal into our water. What was our mass of our metal? Or sorry, not the mass of our metal. The mass of our water. Sorry. 100. What was our initial? Okay. And do we have our final? What? Okay. So let's do some more calculations so we can get that information. So it says, at some point, the metal-water mixture reaches thermal equilibrium at a temperature of 25.35 degrees Celsius. So what, that 25.35 degrees Celsius, what does that need to change up here? Where does that go? This is not 25, it's 25.35. And then we have 25.35 degrees Celsius also. Okay, because it said, at some point the metal-water mixture reaches thermal equilibrium at a temperature of 25.35 degrees Celsius. Calculate the delta T for the metal and the delta T for the water in the experiment. So, if I do my delta T for my metal, that equals 25.35 minus what? 100. I'll do the same thing, my delta T for my H2O, and that will be 25.35 minus what? 25. So what is my delta T for my metal, Valerie? Good. What is my delta T for my water advate? Okay, everybody agree with that? Alright, so it says fill in the blank. Assuming that no energy was lost by the calorimeter, the amount of heat lost by the metal is blank the amount of heat gained by the water. Equal to. Why? Yes. So the amount of heat lost by the metal is equal to the amount of heat gained by the water. All right, E says calculate the heat change of the water. So I'm going to just be looking at the information for my what? Water, not my metal. That's why I think it's important to have all this written out, so that way you're not putting numbers that apply to one thing when you're talking about another. So I'm going to write out my formula. Delta H equals MCAT, and I'm doing this for water. All right, so I'm going to plug in what I have in my formula. What is my mass? Okay. What is my specific heat? And where did you get that information? What? It was given. Good. And then what is my delta T? Okay. So you're going to plug all of that in to your calculator. Erica, what did you get? And my unit? So just joules, because my grams and my Celsius canceled out because we multiplied them by that. What am I forgetting on this? What do I need to have when I have enthalpy? Positive. And why is it positive? What? Because it's gained, but what else? So, again, if you go back, this could either be positive or negative, but we know that it's positive because why? Yes, and also, if you look right here, the amount of heat gained by the water. Aren't we calculating the specific heat change of the water? So even if you had no idea if the reaction was endothermic or exothermic, use your context clues, right? Because something so small as a negative or a positive can count your answer right or wrong. All right, determine the heat change of the metal. All right, so what was our heat change of our metal? Good. Negative 146.44 joules of heat lost by the metal. Oops, not metal, metal. Any questions on F? On how we knew that? How did Jackson know it was negative 146.44? Candace? Yes, exactly. Okay. All right, using the heat change of the metal, calculate the specific heat of the metal. So I'm going to be doing and setting up the same exact thing, except for this time I'm calculating specific heat. Last time I was calculating the heat change, right? Those are two different things. So now I'm calculating the specific heat, but is my formula going to change? Am I still using the same formula? Yes. Delta H equals MCAT. What is my delta H? What do I put there? Negative 146.44 joules equals, what is my mass? Do I have my specific heat? No. What about my delta T? Negative 74.65 degrees Celsius. So everybody plug that in. How many sig figs do we need here? 4. It's always the smallest amount. 2 of them have 4 sig figs, 1 of them has 5. Ian, what'd you get? Okay, yes, and I'm sure you're not the only one. Y'all, I'm teaching you chemistry. I'm not teaching you algebra. So if you don't know how to solve these, you need to come for tutorials because I can't teach you algebra. I'll do it just this once. Okay, you multiply these two together. You get an answer, and that's whatever number, C. You're trying to get C, so you then take that number, and you take negative 146.44 divided by that big number that you got. Yes. Oh, okay, sorry. Thought you had a question. What is it? Am I unit? Joules? Yes. Any questions on that one? Yes. Part what? E? Yeah. Oh, well, I mean, it could be just 146.4. We don't include temperature in that just because it's going to be small. But it was like for Unit 9. I didn't count off for sig figs unless your rounding was wrong. I'm going to do a plus or minus like 1. Does that make sense? Like if you put 147, I would count that wrong. But if you put 146.4, cool. All right. I'm going to, if we have time, I'm going to come back to this problem. This problem is the same exact thing we just did above, but there's other stuff that I want us to go over, and I don't want to run out of time. So that way you have everything for your quiz. Okay, so now we are looking at calorimetry involving combustion and burning. So I want you to just take a moment and look at these two pictures. Take a moment, look at these two pictures, talk with your table about things that you notice with these two pictures. About 30 seconds. All right, let's talk. Somebody tell me some things that you noticed. Yes, Nisha, tell me one. Okay, good. Somebody else. Raise your hand. Tell me something else you noticed. Heather? They're both heating something up. Perfect. Yeah, so simple. Yes. One uses more instruments, one uses not very much. Yeah? What else? What? Same reaction. Okay. All right, so one thing that I want you to notice. Right over here, what is happening? Where is this going? To the water. It's heating it, right? What about here? You have your bomb, your reaction chamber, your fine wire in contact with the sample, and then the cup holding the water, or the cup holding the sample, and then you have your water. This sample is going through the burning combustion. And what do we think is happening with this heat that's happening right here? So here's your cup. What is happening after? It's going out. Think about combustion. What happens in a combustion reaction? Heat is released, right? When I did that demo, the reason I do those demos is not because it's cool. Yeah, part of it is because it's cool. But also is so that way when you think of a combustion reaction, you can remember and think about what you felt if you were close enough. That heat coming off, right? You have your thermometer. We also would have a thermometer here. Okay? One is just more complex and one is more simple. That's basically all it is. But now we're going to talk about calorimetry involving combustion and burning when it comes to solving in math for that. Okay? All right, so a 0.303 gram sample of sucrose was burned in a calometer containing 240 grams of water. During the process, the temperature of the water changed from 22.53 degrees Celsius to 27.55 degrees Celsius. What was the heat change of the sugar? The specific heat of water is 4.184 joules per grams centimeter. Okay, so we're trying to find the heat change of the sugar. So let's write down all of the things that we have. I'm going to draw, and again, it's not because I think I'm good at drawing. I'll be the first one to admit that I'm not. Just so that way we're able to see it. I'm literally going to draw the reaction that's happening. So I have my sugar. Those are supposed to be flames that are burning. What is our mass of our sugar? 0.303 grams. For our water, what was the mass? 240 grams. And our delta T was 27.55 degrees minus 22.53 degrees, right? Everybody agree with that? So now we need to solve. Our delta H equals m cat. I'm going to solve this, even though I'm wanting to find the heat change of the sugar. Why am I going to be solving for water with this? What? I mean, I do know the delta T of water, but what else am I given to solve for water? The specific heat, right? And when I want to know the heat change of something, what do I have to just do? When I find the heat change of water, or the heat that was gained, I can easily find the heat change of the sugar, right? Because it's equal to it. Yes, good. All right, so let's plug all this in. What is my mass? 240 grams. What is my specific heat? 4.184. And then what is my delta T? What is it? 5.02 degrees Celsius. Everybody agree? All right, so everybody plug this in. All right, what did we get? Ira, what'd you get? And that's going to be positive. The heat gained by H2O. So now that we have that, we can answer the question of what was the heat change of the sugar? Yes, Candace. It's what? Is it 5,041? Okay. No? How many sig figs should this be? There should be 3. Yes. Because that's 3. That's 3. Okay. So what would be my delta H of my sugar? Negative 5,040 joules of heat lost by sugar. Any questions on that one? Yes. No. It's just, but I want you to write it down now, just so that way you're able to see it. All right, so to gain some perspective, let's convert this into food calories. This is what a food chemist would do in experiments. That's what I should have done, is become a food chemist, because I love food and I love chemistry. But then I wouldn't, get to teach you guys, so that'd be sad. Okay, so 1 food calorie equals 1,000 heat calories, and 4.184 joules equals 1 heat cal. So let's solve this. So we're going to do stoich, because we're doing a conversion. Woohoo! So we want to find the food calories. So we have negative 5,040 joules. What am I going to put on the bottom? Good, 4.184 joules. And that's equal to what? 1 heat cal. What would I put on the bottom? Good. 1,000 heat cals equals 1 food cal. So plug that in. Josh Raj, what'd you get? Okay. So, okay. Good. Any questions on that one? Yes, Rohan. Say it again. Did everybody else get negative? Yeah. I mean, it's just, it doesn't happen all the time, but it's just with the amount that we were given of sugar, we lost it. Wouldn't that be nice for everything, you know? All right, let's keep trucking along. So very frequently, problems ask us to find the heat of combustion in kilojoules per mole. This is basically a value showing how many kilojoules would be released if 1 mole of a substance burned. So considering the original 0.303 grams of sucrose used, calculate a heat of combustion for sucrose under these conditions. So we have kilojoules per mole, right? So what we have to do is we have our joule value, which was negative 5,040 joules, and we have to convert that to what? Kilojoules. So I have to set up my stoic, and I have to remember my scientific notation equivalents. Okay, so what would I put on the bottom? Good. And what would go on the top? Okay, so that is how we would convert kilojoules, and I'll give you a second to plug that in. And then we have our 0.303 grams of C12H22O11, and we have to convert that into what? Moles. So you need to calculate your molar mass for sucrose. What did we get for joules to kilojoules? Oops. Good. All right, Manil, what's my molar mass? Why? What does Avogadro do for a living? What is his goal? It's for molecules, atoms, and particles, things that we can't see, right? Hudson, what's my molar mass?
342.24.
342 point what? Perfect. All right, so when we plug this in, Sadiqa, what'd you get? What? Oh, okay. Give it to me in scientific notation, because it's a... Okay, so now that we have these, we divide, right? Anish, let me know when you get it. Negative 5.6 what? Okay. Times 10 to the what? Third. And what's my unit? Does everybody agree? Does anybody have any questions? Yes, Hattie.
For B.
For what?
For the B one, I know you're not worried about sig figs, but if we put 1, do we count?
I would count that wrong. Mm. So when I do like a plus or minus, it's like a plus or minus 0.01. So like if you put negative 1.19, probably would count it. But then it's also like the rounding. Like if it was negative 1.23
Right.
and you put negative 1.21, I'm going to count that wrong. But yeah.
Because like the thousand one, it doesn't count, right? That's like
This?
Yeah.
No.
Okay.
Because when we do stoic, we look at the given. That was our given. And that has 3 sig figs. Does that make sense? So then our answer had to have 3 sig figs. Yeah. All right. So last question for the one we've just been doing. I want you to answer this with your table. It says, for the above combustion of sugar, do you think the combustion is endothermic or exothermic? Should heat be listed as a reactant or product of the combustion reaction? And what would the potential energy diagram look like for the combustion reaction? I want you to answer this with your table, please. What? My voice cracked? Cool. Y'all's voices crack all the time. I should start calling you guys out. I'm running on like, let me pause it.